Dear student, now we are going to learn the module titled Computer Architecture and Assembly Language, which has the module code as CSC1344. The facilitator is called Uwera Claire. You are welcome. Now we are going to learn the topic which has the title of Functional Component of Computer based on the Neumann architecture. Functional component of computers based on the Neumann architecture. The Neumann architecture, also known as a Neumann model or a Preston architecture. This architecture was invented by a man in 1945. That man was a mathematician and physicist. That man called John von Neumann. That is why this architecture has his name. The von Neumann architecture comprises the following components. It has a processing unity that contains an arithmetic logic unity and processor registers. It has also a control unity that contains an instruction register and program counter. It has again the memory that stores data and instructions. Later, it has input and output mechanisms. This general description of von Neumann system shows us those different parts using a diagram. You see that you have the part for central processing unit, which has all those inside part. The inner part of the central processing unity, we have the space reserved for registers, we have the arithmetic logic unit and control unit. And on the side, we have main memory, and below you see that you have input and output system. For the subsequent slides, we are going to explain each and every part. The basic concept behind the von Neumann architecture is the ability to store program instructions in a memory along with the data on which those instructions operate. The term von Neumann architecture has evolved to mean any stored program computer. This simply means that a computer which has ability to have the program stored on it along with data, it is called von Neumann architecture. The stored program computer characteristics. Here, this stored program computer has the three main characteristics. The first one is the three hardware system. The three hardware systems comprises with a central processing unit, which you call the CPU, with the control unity and arithmetic logic, and the registers. The registers are the small storage areas, and the program counter. It has also a main memory system which holds programs that control the computer's operation. And it has the input and output system. Those are under the three hardware systems. Remember that the hardware are the physical or tangible part of a computer. The next characteristic, or the second one, it is the capacity to carry out sequential instruction process. This sequential instruction process means that the machine designed under the von Neumann architecture or under the von Neumann model, it processes the instruction or the data in a sequential way. The instructions are processed one after another one, not in parallel, it is in a sequential. Also, the last characteristic is that it has a single data path between CPU and main memory. The single data path, you know that the data to pass through the computer need to pass through the buses. So it has a single data path between the CPU and the main memory. This single data path is known as a von Neumann bottleneck. It means that it is its disadvantages of this model. Means that data and instruction has to pass in a single data path. Means that the data, if the data is passing, it has to wait for the instruction. Then the instruction comes after the data. It means that it uses a narrow or a small path. This leads to the disadvantage of this model because it can take a long time to execute instruction or to deliver the data on time. The following quizzes will support and help you to understand more for the previous slide. Good. Now, let's try to see the problem of a Neumann model as I was just explaining for the previous slide. CPU's processing speed is much faster in comparison to the main memory, RAM. As a result, the CPU needs to wait longer to obtain the data read from the memory. As I told you that they use a single data path where the data should pass either after the instruction or instruction passes after the data. This CPU and memory speed disparity is known as von Neumann bottleneck. It means that CPU waits for the instruction to be taken from the memory, and also CPU waits for data to be brought from the memory. This takes a time so that the time the memory to give the data, the CPU may be idle. So means that the speed of the memory and the speed of the CPU to process, it is inequality. So on that time, there is a disparity. This is the problem of this model. Now let us look at the part of the CPU, which is in full central processing unit. The CPU, which can be considered as the heart of the computing system, includes three main components. The first one is the control unit, in short is CU. The second one is one or more arithmetic logic unit, and the last one is the various registers. Let's start to see one by one and see the more explanation and the law or the function of each component in the process of instruction. The control unit is the policeman or a traffic manager of the CPU. The control unit determines the order in which instruction should be executed and controls the retrieval of the proper operand. As I told you that the CPU is the heart of the computer. So one part of the CPU is designed to control or to determine the order to retrieve or to get the instruction and the way that instruction will be executed and the proper operand needed for execution of that instruction. The second one, CU, is interprets the instructions of the machine. The role of the control unit again is to interpret the instruction of the machine. Is this instruction needed on this time? What is the role of this instruction? What is the operation? What is the purpose of this instruction? It is reserved for the control unit to coordinate all those issues. The execution of each instruction is determined by a sequence of control signals generated by control unity. Means that the control unity works by sending the control signals to determine, to show which instruction and what is the purpose of this instruction by sending the control signals. With those control signals here, generated by control unity, the control unity handles all processor control signals. It directs all input and output flow, fetches code for instructions from microprograms, and directs other units and models by providing control and timing signals. The control unity provides the control and timing signals to show which part of instruction needed, the code or the block of code needed to execute and to perform the operation. The types of control signals. These signals are used to identify the nature of operation. There are three control signals. The three control signals are RD, which stands for read. The second one is WR, which stands for write. And the last one is the ALE. This ALE, we'll see it is for address latch enable. Let's try to see the explanation for each control signal. RD, this signal indicates that the selected input or output or memory device is to be read and is ready for accepting data available on data bus. You know that the data and the instruction should pass through the data bus. So now on that time, this signal will show the CPU which data to be read, which memory to be read, so data will be retrieved from that area. And then if the select input output unity, it has to show which input part needed or output part needed. It means that it is used to show it is for input output unit needed or it is memory device needed to be read. The WR, this signal indicates that the data on the data bus is to be written into a selected memory or input-output location. Means that also this WR or write signal indicate that the data on data bus is to be written through or from the input-output system or the memory location. The last one is ALE. This is a positive going puzzle generated when a new operation is started. If there is a new operation, for example, it is for addition, it is for subtracting, it is for moving, this is the operation to be done. If the new operation is started by the microprocessor, this ALE should be enabled. When the parser goes high, it indicates address. And when the parser goes down, it indicates data. It means that it has two options, on and off. If it is on, if the parser is on, it means that it indicates the address of data. If it is off, it indicates that it's data to be read, either address or data. Address or data. On is for address, off is for data. The arithmetic logic unit as the second component of CPU. An arithmetic logic unit is a combinational digital electronic circuit that performs all mathematics or all mathematical and Boolean operations. Assume that you are going to calculate, for example, the perimeter of rectangle. On that time, we need to perform the arithmetic operation. On that time, the ALU will be used. Generally, an arithmetic logic unit has two inputs and one output. The input to an ALU are the data to be operated on, called operand, and a code indicating the operation to be performed. Those are the two inputs for arithmetic logic unit. It will need the data to be operated on and the operation to perform on those data. The output of this arithmetic logic unit is the result from the performed operation. I think it is understood. So now it is time for the quiz to help you to understand more. You can read through and then you answer the questions. And I hope that you enjoy with the reading and doing the quiz. Right. Let us look into the processor register. The registers are the temporary storage locations to quick store and transfer the data and instruction being used. I repeat again, the registers are temporary storage locations to quickly store and transfer the data and instruction being used. Example of registers: the program counter, instruction register, program counter, accumulator, and so on. Because the registers are often on the same chip and directly connected to the CU, the registers have faster access time than memory. Due to the space from the register to CPU and from the memory to CPU, the register is very closer to CPU. That is why the CPU accesses frequently to the register. Therefore, using registers both as a source of operand and as destination of result will improve the performance of the machine. After knowing those different parts of CPU, there is a cycle which explains the full function of CPU. That cycle shows how the data will be retrieved or taken from the memory and how the data will be decoded and executed. The control unit fetches the next instruction from memory using the program counter to determine where the instruction is located. As you see the diagram shows the central processing unit with their parts, program counter and the control unit. The control unit here fetches the data from main memory and brought the instruction from the main memory. Then the instruction is decoded into a language that the arithmetic can understand. The control unit takes the data from the main memory and brought to the arithmetic logic unit. Any operand required to execute the instruction are fetched from memory and pressed into registers within the CPU to be processed. The arithmetic logic executes the instruction and presses the result in a register or a memory for later use. So with the brief diagram that will help you to memorize the fetch, decode, execute cycle, here you see that you have a triangle from the control unit to the arithmetic logic unit. We have random access memory and the registers. Remember that the control unit will take the data from registers. Those data from registers will come from the RAM. Then, if the data or the operand and the instruction to operate on it are needed for logic or arithmetic operation, will be brought to the arithmetic logic unit. This is the boss of execution. And then later, the control unit also decode the instruction to know which the purpose of the instruction brought. Thank you for following me on this session. See you for the subsequent slides. Thank you.